Okay, let's go. So where did we end last week? Ah, okay, on the product diagram. Oh, and I switched to the notation with brackets.
Yep.
Okay, so I'm going to stick with that. Perfect. Okay, so this was the end. Last week we proved this fermionic-Wick rule for at least the 4-point function, the spin-spin correlation on the boundary. Let me now give you a last application, like trivial kind application of the random current, and then we prove a more substantial theorem. So the last proposition of this section is devoted to another inequality, which is the following. So imagine let S be, or let's say A, be a set of, containing 0. And let's take X not in A. Okay. Then I'm going to have, so what is going to be the simplest way of writing it? Sigma 0, sigma x is going to be smaller or equal to the sum of y in A and z not in A of sigma 0, sigma y, sigma z, sigma x. And here I'm going to put a hyperbolic tangent of beta j y z. So this is called Simon's inequality. And I'm going to prove it. I'm going to prove a slightly different inequality. And in fact, let me even give you the true one. So the true one is that here you can even add that you look at the small graph. So what does it mean? It means you have 0. You have a set A. Okay. You have X, which is not in A. And you can imagine A is some kind of separating surface between 0 and A and X, meaning that if, for instance, for percolation, you would have a path from 0 to X, it would have to exit at some Y somewhere by an edge going to a certain Z. So what this thing is telling you is that the correlation between 0 and X is smaller than the correlation between 0 and Y in the set A times the correlation between Y and Z in the set which is just given by the edge YZ. And this is going to be this hyperbolic tangent. It's a weight which arises naturally. And there you have a path from Z to X. Okay? I'm just thinking maybe it's not hyperbolic tangent. I'm always... No, it is. Sorry, it is. So this thing, we are going to prove it in an exercise for next week. Or for the week after, I don't know yet. Let me prove to you a slightly simpler one in the nearest neighbor case. Okay? So in the nearest neighbor case, so basically the proof would be the same in both cases, but here I'm going to simplify a little bit. In the nearest neighbor case, I'm going to prove that sigma 0, that for any S separating 0 from X. And this is actually the original Simon's inequality. This is an improvement over it, which will be useful for the next proof. But here, this is the original. You take 0, you take X, you take any set which is separating 0 from X, in the sense that if you want to go from 0 to X, you have to go through a vertex in S. And then what you get is that sigma 0, sigma X is smaller or equal to the sum of a Y in S of sigma 0, sigma Y, sigma Z. So you see this, sigma X, sorry. So this one compared to this one has two improvements somehow. The first one, first it works for infinite range. So there is this additional hyperbolic tangent which is taking this into account somehow. And one very important improvement in this one is that you can restrict the small guy to be actually in A. Like you are just looking at correlations in A. Here it's really in the full plane. Okay, let's try to prove that. So let's look at the right-hand side and see what we can do. So the right-hand side, sum for y in S of sigma 0, sigma y, sigma z. This is 1 over z of the empty set squared. You remember, like the partition, the sum of the sourceless currents, times sum over y in S of z of 0, y, z of y, x. This is still an x. I don't know why I absolutely want it to be a z. Like that. And now what do? You do a switching lemma. Now you get used to this thing. It's always the same type of ideas. Z of empty squared, and you get sum over y in S. But now you're going to get z of 0. So here you have sum over currents N1 with sources 0 and x, and sum of a sourceless current for the second one of the indicator of W of N1, W of N2 times the indicator, then 0 is connected to y in N1 plus N2. Okay. Very good. So let's now divide all of this. Let's make this quantity happen. So it's going to be sigma 0, sigma x. It occurs like that. And then I get the sum over n1 equals 0x, n2 empty set, wf n1, wn2 times the sum over y of the indicators, and 0 is connected to y in n1 plus n2. Okay, this I just exchanged these two sums. And because I made the sum of currents with sources at 0 and x appear, and I divided by the one with sourceless, here I get the sum of n1 equal 0x and n2 equal empty set. Are you all okay with that? So basically I divided and multiplied by this sum over n1, and therefore I make this thing appear. But what do I observe on this thing now? This is the expected number of points in S which are connected by n1 plus n2 to 0 for n1 plus n2, which is what? Which is just n1 is a current with sources at 0 and x, and n2 is an independent current with no sources at all. But if there is a current with sources at 0 and x, necessarily 0 and x are connected in n1 plus n2. Therefore, there must be a point, because I'm dividing a separating set from 0 to x, there must be a point, at least one, in S. So this quantity is necessarily larger or equal to 1. So I get that this thing is larger or equal to sigma 0, sigma x. And that's the end of the proof. Okay? You should think of this Simon's inequality. It's basically giving you what BK was giving us, what the Vandenberg-Kesten inequality was giving us for percolation, that if I need to be corrected from 0 to x, I need to be corrected to 0 to a certain y, and from y to x. And there, what we were using is disjoint occurrence to say, okay, then the probability of that is smaller than the product of the two probabilities. And here, for Ising model, you don't have this disjoint occurrence thing, but you can replace it by the Simon's inequality. The existence of this Simons inequality is basically why we are going to be able to prove the sharpness of the phase transition here as well. Somehow you need either the BK or this Simons inequality to do it. Okay, that was the end of the proof. In order to prove really the more advanced Simons inequality, you need to dive a little bit more into random currents, introduce what we call the backbone of a current. You will do that in your exercises. Or you will not do it, I don't know. Okay. What is the corollary of that, then? The corollary of that, or maybe let's put it in a new section, so see sharpness of the phase transition. And let's start by a corollary. The BK inequality, what was it implying? It was implying that if I introduce this phi p of s, if for some set s, the phi p of s is smaller than 1, then I have exponential decay. So here, something similar is going to happen. So introduce phi beta of a set S to be the sum for x in the set S, y not in the set S, of hyperbolic tangent of jxy beta times sigma 0 sigma x in the set S. Okay? And with free boundary condition. Maybe I didn't put free in the, and I just said if there is nothing, it's free. So let's, okay, introduce this. Notice that it looks very much like the phi p of s of percolation. So remark, looks like the phi p of s of percolation. How was it defined? Remember, it was a sum for x in S, y not in S, of p times the probability that 0 is connected in S to x. And what am I saying? Okay, no, it was for every xy in delta S. That's how it was defined. Okay? So remember, I mean, notice two things. So this thing is what? This is exactly like the spin-spin correlation between 0 and x in the set S. It's like, okay, I think that I do not have all of ZD, I only have the set S. Am I connected? Is 0 connected to x or not? In the framework of geometric representation, it's exactly the spin-spin correlation. So this term here is this one. Now, remember in this case, we were looking at nearest neighbor model. For nearest neighbor model, the P and the condition that x and y are an edge on the boundary is exactly, you could replace that by the probability that the edge xy is open for an x in the set S and a y not in the set X. And then you get exactly the same thing. This should really be interpreted as probability of being open, basically. So it's exactly the same. In fact, if you prove for percolation in the non-nearest neighbor case, you are going to get exactly a sum. It's going to look even more like that. You are going to have a sum for x in S, y not in S, and here you should put 1 minus exponential of minus beta jxy. So you really, which is exactly probability that the edge xy is open. So it's really, really the same quantity. Okay, and therefore what is not surprising, so corollary or proposition, if there exists a set S such that phi beta of S is smaller than 1, then what do you want to say? Well, you want to say there is exponential decay. The problem is, let's be careful here, we have infinite range. So exponential decay a priori is out of the question. You're not going to be able to prove exponential decay. Imagine that jxy is decaying like 1 over the distance squared or something like that. You will never get exponential decay, right? So here, what you are going to prove is something a little bit weaker somehow, which is that the sum for x in ZD of sigma 0, sigma x, beta is finite. It's what we call finite susceptibility. And if jxy is finite range, then indeed you get that sigma 0, sigma x, beta smaller than exponential of minus c x for some c which depends only on beta. So you get, morally, what I'm get exponential decay is just that in infinite range, exponential decay is not really what you are looking for because it's not holding, but it's just the finiteness of the susceptibility. So let me try to prove that to you. And because we already did the finite range, and I will let it to you to try to prove this finite range, that in the finite range you have exponential decay, I'm just going to focus on the first claim, that you get finite susceptibility. Okay. So let's look at chi n of beta is going to be the supremum over x in lambda n of the sum for y in lambda n of sigma x, sigma y. And I drop the beta is fixed. Okay. So I'm taking the biggest point from which somehow the average of the spins, the point for which the average of the spin is the biggest. I look only at the box of size n because I want to be certain this thing is finite. And now I'm going to use here exactly the Simons inequality I just erased. So what I'm going to do, I'm going to say, okay, this is, so chi n of beta, like this. So this sigma x, sigma y is smaller or equal to the sum for z in x plus s, so in the translate of s, of sigma x, sigma z, sigma y, and I get here a hyperbolic tangent of beta j y z. But now here, what do I notice? The sigma x, sigma z, hyperbolic tangent, blah, blah, sum over z in x plus s, by invariance under translation, this is just phi beta of s. So this is smaller or equal to phi beta of s times or let's say, now I sum over x, sum over y. I get that this is smaller, that's phi beta of s, times the maximum of the sum over z of okay, what am I doing? Sorry about that. So this is for y not in x plus s. Sorry. So now when I sum over y in lambda n sigma x, sigma y, I get, first I have the sum for y in s, and then I have the other sum. So for y not in S, I can use these things. So And then I have this. So this is just phi p of s. So here this is bounded by just the cardinality of s, because this thing is smaller than 1. And here this is bounded by sum for y not in s. Here I get phi p of beta of s, and I get sigma y, sigma z. So what did I get? I get that this is smaller than cardinality of s plus phi beta of s times what? Times something which is definitely smaller than chi n of beta. Okay, because this thing is smaller than the sum of all the y in the thing, and I must have exchanged a y and a z somewhere. No? No, yes, so it's the sum seen from z, and there is something wrong in what I wrote. Oh, yes, you just need to exchange the y and the z, and then you get the chi n of s, and then, okay. Wait, that's elementary, yeah. That's why it's elementary, that's the reason why I cannot do it on the board. So you get this inequality, so what now you maximize on x, and it gives you that chi n of beta is smaller or equal to cardinality of s plus phi beta of s chi n of beta. And this gives you that chi n of beta is smaller than cardinality of s divided by 1 minus phi beta of s, because phi beta of s is strictly smaller than 1. Okay, now you let n tends to infinity, and you get what you want. Okay, so the susceptibility is necessarily finite. There is something about what I'm doing here that it doesn't depend on the graph. So you can even take a graph, which is, say, non-amenable. You can take a tree, you can take... And there, you see the finite susceptibility is actually not even comparable. It's not weaker or stronger than exponential decay. It's just a different quantity. If you take a graph which grows exponentially fast, it's going to tell you that, indeed, the correlations are decaying exponentially fast. On ZD, it doesn't tell you that. It's weaker than that. But so there is something interesting there. Okay. Why did I do that? Because exactly like for percolation, now it becomes natural to define. So let's define beta C tilde, which is the infimum of the beta, such that phi beta of s is larger or equal to 1 for every s. Okay? And what is our result? What is going to be our guess is that beta C tilde is equal to beta C. So theorem, beta C tilde equal beta C. Furthermore, if I look at sigma 0 plus beta, if I look at the magnetization, above beta C is going to be larger than square root, and let me try to get the right constant because it's actually a nice one. It's going to be square root of, I think, beta minus beta C divided by, yeah, perfect. Square root of beta C squared minus beta C, beta squared minus beta C squared divided by beta squared for every beta larger or equal to beta C. What is the important thing on the second one is that, so let me give you a few remarks before diving into the proof. So first remark is that it shows that sigma 0 beta plus grows like, larger than a certain constant times beta minus beta C, square root of beta minus beta C. Remember, for percolation, we got larger than constant times P minus PC. Here it's the square root. And this is also the mean field exponent. So I told you for percolation, this is actually the exponent that you will get on a tree and so on. Here it's going to be the exponent that you get for, on a tree or on a large lattice. So this is the mean field lower bound. So there is something you are going to see. The proof is, in fact, up to now, the proof looks very much like, it starts very much like it was starting for percolation, right? We introduce the same quantity. We have the same case that if for some set S it's smaller than 1, then we have exponential decay or finite susceptibility. You will get exactly the same thing if you take long-range percolation. You will also prove finite susceptibility. And we are going to get also the mean field lower bound. So there's something kind of universal in these two proofs. That's the same proof. That's the first remark. The second remark is, because beta c tilde is defined like that, at beta c tilde, which is beta c, we have that. So at beta c, phi beta of s is larger or equal to 1 for every set S. Okay? And this you can easily check that it implies that you do not have finite susceptibility. So this implies, exactly like for percolation, that the sum over x in ZD of sigma 0, sigma x is infinite. Simply sum, because this guy is up to constant, it is larger than the sum for n in n of phi beta of lambda n, roughly. So, because all of these terms are larger or equal to 1. So it tells you, in particular for finite range and things like that, it tells you something which is known for a long time via Simon's inequality, which is that at criticality for the Ising model, you do not have exponential decay. And in fact, you even have polynomial. The last thing is that this result is not due to us. So this proof is due to Vincent and me. But the proof, the original proof was due to Eisenman, Barsky, and Fernandez. Basically in the same generality, in the sense that it's not exactly in the same generality, but it can easily be extended to the same generality. But I'm going to present this proof because it's simpler to present. The other one has a few advantages, but here we will not use them. Okay, so our goal is to prove this theorem. So what do we want to do? We want to do exactly the same as what we did for the other, for percolation. We are going to try to derive a differential inequality. And you are going to recognize exactly what we want to do. So what we will get is that the derivative in beta of sigma 0 plus in the box lambda, so you let lambda be a finite graph. So the derivative of this thing is larger or equal to the infimum over the set S included in lambda and containing 0 of the phi beta of S times 1 minus sigma 0 plus lambda. So if I do that, I get exactly, this is exactly what I was getting for percolation. Exactly the same. But here, what we are going to get is that it's the derivative of the squares, and it's expressed in terms of the squares. That's going to be what we prove. So exactly the same differential inequality, except that it's involving the squares of the thing. And you're going to see the analogy goes farther than that. It's really, somehow, we found the proof for percolation, But then it became very clear that it had to work for Ising just because it was too good to be true. Like it was too, everything was looking exactly the same somehow. Then the details are going to be a little bit nastier, but this is a complicated paper to read, and it's a complicated proof. So, okay, it's not going to be a very simple proof what I'm going to explain to you, but still, I think it's worth having. Like I think you couldn't teach the other one. It was too complicated. So this here, I'm going to try for the first time to teach it. Okay, I'm not going to integrate this thing, but you see now that if beta is larger or equal to beta c, you can integrate that, and you are going to get what you want. Okay? If beta 1, you integrate to get what you want. So in fact, I'm cheating, but just cheating for technicalities. There is a small additional factor here, which is that, in fact, in the inequality, you need to add an additional term, which is not very, very nice. Here you need to add a 2c of lambda divided by beta, where c of lambda is, I'm hesitating whether I tell you what it is or not. Okay. So in fact, careful, so there is a c of lambda, which is equal to the infimum over y in lambda of sigma 0 lambda plus divided by sigma y lambda plus. So somehow there is a kind of finite size correction. Let me just tell you that this is absolutely irrelevant in the proof. So what we are going to do, you are going to allow me to do that. We are going to look directly in infinite volume, which a priori you cannot do because you don't know that the quantities are differentiable. And I'm going to sum over currents, weighted currents, directly in infinite volume, which has no meaning because, all the sums are infinite. But in fact, the manipulations are exactly the same in discrete, and I'm going to tell you exactly the place where this C of lambda appears. But let's ignore this C of lambda. And the only thing I need to tell you is that this C of lambda is not problematic because it tends to 1 when lambda goes to infinity. Just that. So somehow it's just the natural quantity is the infinite volume version. It's just that for percolation, everything is independent. So you can work directly in infinite volumes. There is no problem with that. Here, it's, you have this tiny technicality, but this technicality is, in the original paper, if you would have had this technicality, you would have just ignored it and say, okay, it's clear that, and that's. So let's work directly in infinite volumes. So for ease of presentation, I'm gonna just take lambda equals ZD and just work in this, and then C of lambda, I'm going to also take it to be equal to 1, because you see, I'm going to tell you in this case, you don't need to introduce the C of lambda, and I will really tell you where the C of lambda is in fact occurring in infinite volume. But the philosophy is the same. Okay. So let's start this. So, how do we write the derivative? So let's start with the derivative of just of sigma 0. Okay. And same thing, do I ignore the h? I'm going to ignore the h. Yeah, it's better. So if I differentiate this, what do I get? So this is easy. It's the sum over every xy of sigma 0, sigma x, sigma y, minus sigma 0, sigma x, sigma y, and I have pluses everywhere. And this is for every xy, and there is, sorry, a jxy. Okay? This is exactly what you will get if you differentiate this quantity. Now, I can use the switching lemma. I mean, this I already mentioned, this type of quantity can be expressed in terms of random currents. And I can use the switching lemma in there. Okay, I see that people are doing like that. You remember that last week I exactly did this manipulation. And this, in fact, would be equal to the sum, so 1 over z of the empty set squared, sum over xy, jxy, and here this thing, I could look at it at z, I mean the sum over a first current and a second current. The second current will be with empty set, and the first one will have sources 0 and the ghost that I called delta, I think, last week, right? Symmetric difference with xy of w of n1, w of n2, and the indicator that 0 is not connected to to delta. Okay, let me just recall one last time how I do that. Remember that this is the sum of the currents with sources 0, delta, x, and y. Usually I was not putting delta in the sources. I was just telling you, well, you know, I just look at the sources on the graph. But here, just to illustrate really that delta is here, I'm going to put it, okay? So 0, this is exactly the sum of the sources 0, delta, x, and y divided by sourceless currents. I was multiplying by z of the empty set and divided by z of the empty set. This was the sum of the guys with sources 0, delta, and here's sum of the guys with sources x, y. What did I do? I switched the sources from 0, delta to the other set. So this guy was the sum of, indeed, these sources, but there is the indicator that 0 is connected to G. So since I'm doing this thing with no indicator minus the thing with an indicator, I get exactly that. Okay? Very good. So let's say that this is roughly, I'm going to write it as 1 over z squared, z of empty squared. And here I'm going to sum our xy, I mean x and y. And this quantity, I'm going to call it delta xy. This is this quantity. Okay? And notice also one thing, that here, I have sources at 0, at x, at y. I'm going to always draw them neighbors just because it's simpler for the intuition. And at delta, which is basically it's this ghost vertex which is lying above everybody. But notice that if there are sources at these places, and if 0 is not connected to delta, then what is the only possibility? 0 has to be connected to x and y to delta, or the opposite. And x and y cannot be connected together. Okay? So in fact, what I'm going to add here, I'm going to just, because here I'm not telling, I'm summing over pairs, I'm going to sum over x, sum over y, and the delta xy is going to be this thing. So jxy sources wn1, wn2. But I'm going to add in the indicator that 0 is connected to x, y to g, and 0 is not connected to g, delta. I'm going to make this mistake more than once because I'm used to call it ghost. No. So here, the only thing I did is that I just, in the pair xy, I said that x is the guy connected to 0 and y is the guy which is not. So now I really have this picture. Okay? In terms of currents, that really means in the sum of, and this is always in the sum of the two currents. It really tells you that 0 is connected to x, y to delta, and not together. What do you recognize here? You just recognize the quantity, I mean, the probability of being pivotal for percolation. You have exactly the same picture, exactly. So it's not surprising that everything we are going to do after that is going to just be manipulations which end up at the same place, just because this is the same picture. But now, instead of having percolation, we have sum of two currents. And it's not surprising, sum of two currents are related to the square of connectivity properties. So it's not surprising that instead of having probability of being connected, we have the square of the spin-spin correlation. Okay, so that was the beginning of the proof. Now let's do, you're going to see it's going to be a little bit painful, but not too long. So that's so first claim, which disappears here. So what are we going to do? What we are going to first do is try to simplify a little bit delta xy. And for that, we are going to condition on the set S0, which is a set of vertices Z, such that Z is not connected to 0 in N1 plus N2. Okay? So this was exactly the set we were conditioning on in the case of percolation. So if we condition on that, we get that this is here the delta xy is a sum over S that doesn't contain 0 and x, right? That's the condition. And S has to contain y and z, y and delta. Then I still have the sum over N1 with sources 0, delta, and xy, and N2 with sources empty set. Maybe let's, oh no, omega N1, omega N2, and then indicator that S0 is equal to S. So this is exactly the same, because just the fact that this indicator here, on this event, it's exactly, I translated by this and this. Okay, so this delta xy, when I sum over every set S, is the same. Good. So now, claim 1 is that you can simplify that. So for any set S which contains y and delta and such that 0 and x are not in S, we have. So I'm going to change a little bit this horrible thing. So the sum over currents of this, I'm going to write it as 1 over sigma 0 plus, and then I sum over N1, which is 0 x, and N2, which is the empty set. Over Wn1, Wn2, and here I still have the same indicator, except that I'm adding that y is connected to G in N1 plus N2. So what did I do here? I removed the sources y and delta. At which cost? At the cost of adding this term, which let's call it sigma y, just to illustrate a little bit more, sigma y. So what I did here is that I removed these sources, y and delta, and the cost is that I'm getting a sigma y like that. And here, it's an inequality. So that's the first claim. It's not surprising, right? I mean, if you think about it, it's not very surprising because it's exactly, I mean, this source is exactly something which is involved in this sigma y. The cost, I mean, what may be surprising at first when you look at it is that it's divided by and not product. But remember that here you have y connected to g that occurs. So from the switching lemma, it counts a little bit like twice, like sigma y squared. So already here you should think, these terms account for sigma y squared. I divide by sigma y, I should get exactly one sources at y and g. And that's exactly what occurs. Okay, I realize this is, let me, oh yeah, because you are going to suffer so much otherwise. Let me first prove this claim and then we make a break. That will be a good break. Okay. So let's call this thing theta, the first guy. So notice that when you condition on S0 equal S, so this is S. This is somehow this guy is the exterior most, like the boundary of S is somehow the exterior most blocking surface. I mean, surface for which you have zero current. So the current N1 and the currents N2, they are somehow divided, like they are divided in two currents. There is the current N1S and N2S, which is defined on S. And there is a current N1S complement and N2S complement, which are defined on the complement. Because there is no, if you take an X in S and if you take an A in S and a B in not in S, anyway the current between them is zero. Okay? So we are going to decompose exactly on that. We are going to say, okay, write N1 as N1S plus N1S complement, and same thing for N2. Okay? And let's, now this thing you have W of N1, which is W of N1S times W of N1S complement, and same thing for 2. Okay? Well, just expand the whole sum. Like, just replace N1 and N2 by these guys. So it's going to be a huge sum, but not that ugly. So you're going to get the sum over N1S, N2S, N1S complement, and N2S complement with some sources. I let you guess which ones they are. You have the W of the 4 guys. And you have this indicator of S0 equal S. So what I'm going to do, I'm going to put N1S alone. I'm going to put it here. Sum over N1S. And what are the sources of N1S? Well, N1S is a restriction of N1 to the complement, so I should not have. So N1S is the sum, is the current on this thing. So the sources are Y and G. Like that. Good. So how can I express that with the source? How can I make the source disappear? Well, it's not very difficult. I can make the source disappear if I pay a very explicit term, which is just sigma y s. Sigma y s is equal to that divided by the thing with sourceless. So I just do that. Good? So this was theta. Now let's multiply theta by sigma y s. What do I get? I get a square here. Okay? Now, N2S, let's add it here. I'm going to do it like that because you should not really write. I mean, I think you can just, at this point, just try to follow the manipulations. And I mean, it's sufficient that I suffer. You don't need to suffer with me. And I don't suffer when I write that because I'm very happy with this proof. So anyway, okay, you have that. But now here, this should screams to you, okay, I have two currents. Let's just use the switching lemma because I want to have y connected to g in the source. So let's exactly do it. Let's replace this by yg, replace this by yg at the cost of nothing. What did I do? Ah, sorry, no, I did one step too fast. So now this is sum over n1 s complements, n2 s complements. And here you see you have sourceless, sourceless. Here you have the product with sources divided by sourceless. So this is exactly the same as sum n1 s yg, n2 s yg of w n1 s, w n2 s. Okay? There, I mean, I made one split that, I mean, I could have gone a little bit faster, but Vincent tells me it's better that way. So faster is not always better. Good. We have that. Now here it really screams to you switching lemma. So let's switch the sources. Here I put n1s, n2s, but that's the same as n1 and n2. And now what do I observe? Well, I can recombine everybody, right? If I recombine n1s, n2s, and so on, I just get the sum over n1 and n2 with the right sources. I'm not going to write it. Oh, well, let me write it. So now n1, the sources are the sources of this guy, which were 0 and x. But now there is no sources in this guy, so these are the only two sources. N2 is still sourceless and sourceless, so that's perfect for us. And we get the weights they get together, and we get this. And that's exactly what we wanted. No, that's not exactly what we wanted, sorry. So this was theta times sigma y sigma s. I wanted theta times sigma y plus, and there was a plus. That, I mean, these guys are with pluses, of course. But here, this thing is, of course, smaller or equal to theta times sigma y plus. The fact that I'm restricting myself to s is reducing the current. And here, what did I do? I cheated you. Why is it the case that I cheated you? Because here, it's not true. I make S get bigger, true, but if I take plus boundary condition on the boundary of S, this is a much stronger push. In fact, the inequality is going the other way around. Bad Hugo, right? In fact, the thing is that you don't want to work with plus. You want to work with what we call external field, but I didn't want to introduce that. So if you work with external field, it's not more complicated. Nothing is more complicated. It's exactly the same manipulations, virtually the same manipulations. There is not a single line which is changing. And then this inequality is true here. So that's the first cheating that I allow myself. And I'm going to allow a second one in a minute. I mean, in 15 minutes, like that. OK, let's make a break and start again in 25 minutes. But really, the idea is the same. The idea is really the same. So? OK, so I propose to start again. So this claim 1 has a very natural interpretation, which is that it corresponds to removing the source y, right? You remove the source y in this thing. This guy has a source at y, I mean y and g then, because they go together. And you get to no sources at all for this. Now the second claim, what we are going to do in a minute, is actually removing the 0 and x, the sources 0 and x. But before that, let's just see how this thing translates. So now we are up to this point where we have delta of xy is larger or equal to 1 over sigma y plus, and you get the sum over S containing sum over S, the sum over N1, which is 0x, and N2, which is empty set, of Wn1, Wn2. And what I'm going to do, instead of saying, so when we were summing here, we were summing, now y and delta are disappearing, so we were summing 0 and x, and we are going to just, instead of saying that S must contain 0 and x and not y and g, I'm going to just re-include them in the set like that. So I'm going to say 0 and x are connected, are belonging to S, sorry. Y is connected to G, to delta in N1 plus N2, and 0 is not connected to delta in N1 plus N2. So this is just what you get when you replace this thing by this thing in this. And now what I'm going to do, so there is no S0 anymore. So what I'm going to do, I'm going to define S delta to be the set of Z in ZD, so that Z is not connected to delta. And this is exactly the set that we were introducing for percolation. This one is exactly the set that we were introducing for percolation. So now when I look at this horrible thing, I get sigma y plus, and I get the sum over S, and 0 and x are in S, and y is not in S, of W of N1, W of N2, and the indicator that S delta is equal to S. So this thing is exactly equal to that. And there is still the sum over N1 equals 0x and N2 equal empty set. Okay, so whatever, the important thing for you is that you can now rephrase everything like that. Just you have sources at 0 and x and no sources for N2. So you condition now on delta, on S delta. So my claim 2 is going to be removing the sources 0 and x, that I really get to a sourceless current. So claim 2. Is going to be that the sum of this horrible thing is equal to the sum. I'm going to put now sourceless currents I still keep these things, but now I'm going to add indicator. Sigma 0, sigma x in S. So that's the cost we are going to pay. And once again, almost like a dimensional analysis, we see that this is coherent because here we had sources 0x. If you go to no sources, you pay something like that. And that's actually what I have. Perfect. So how do we prove that? We do the same thing. We divide between N1, N1S complement, N2S, and N2S. I mean, actually, maybe we only need to do it for N1. We are going to divide between N1S and N1S complement. So you get sum N1S complement empty set, N2 empty set, N1S complement, and 2 indicators that S delta is S. And then you get the sum over N1S equals 0 and x. This guy has sources at 0 and x. Okay, this is exactly the guy on the left. And here, what do you observe? Well, this is exactly, if you remove the sources and you put empty sources, then you are just multiplying by sigma 0, sigma x, s. And that's all. Then you recompose and you get the right field. Okay? Now, let's recombine everything together. So what do we get? So this first gives you that delta xy is larger or equal to 1 over sigma y plus. And then I get the sum for S containing lambda, for S, sorry, containing 0 and x, S not containing y, of the sum. Now the currents are sourceless, which is perfect for us. Wn1, Wn2, sigma 0, sigma x, beta, and we get the indicator as delta equal S. Sorry. Okay? This is a combination of everything. So notice that we first, there is something a little bit strange that we had. So we had this delta, which was actually having a fairly good structure. We could have right away conditioned on S delta and try to do exactly what we would have done. So forget about all of this. Imagine we were at the very beginning with the delta xy, and we want to really do exactly like percolation, right away express this with, condition on S delta. The problem is that there, remember, you are going to see we were dividing by the partition function for sourceless currents. So we didn't have a good interpretation because we had currents at the top with sources 0, delta x and y and empty for the other one. And we were dividing by currents with no sources at all. So we didn't have a nice probabilistic interpretation. So this was not very nice. So the goal was, okay, first we need to remove the sources. Let's try to remove the sources on the top. So the claim 1 was we remove the source y and delta. Claim 2 was, and for that we had to do something which doesn't sound very natural, which is conditioning on somehow S0, which was the point that, which is not the complement of S delta. Be careful, it's not the complement of S delta. So we had to condition on this S0 to remove the sources at y and delta. And then, really, we could finally condition on S delta, remove the sources, and now you're going to see the manipulations are going to be nice. We are going to get exactly like what we were doing for percolation. Now it's somehow exactly the proof for percolation. But there was this thing that you needed to, but for good reasons somehow, because it's, otherwise you will not, at the end you end up with exactly the quantity that you had for percolation. So, but you had to pay somehow, to suffer a little bit and try to remove the sources first. So now let's really look at what we are interested in, which is this quantity squared. So this is twice sigma 0 beta plus d sigma 0 beta divided by d beta. I realize that maybe I forgot the 2 in the lemma. Sorry, I'm going to add it myself at the end. So this is larger or equal to 2 over z of empty set squared, sum over x and y. So let's write sum over x, sum over y, and I had the delta xy. Okay, so the delta xy was j xy times, oh, I forgot the jxy. The jxy disappeared somewhere. And you have to put it everywhere. Let's check. It disappeared also in the article. Wonderful. Well, that's just one more typo. What can you do? Anyway. Okay, so you have this huge sum. So you have sum over sourceless currents. Wn1, Wn2, sigma 0, sigma x, s, indicators and s delta equal s. Now the sum over s, I'm going to put it before. I'm going to put the sum over s containing 0. So then I want the x to be in s, and I want the y not to be in s. And notice that this quantity here doesn't depend on the current, so I'm going to put it here. Okay? Now, first manipulation, this thing, put it here. Okay. Second manipulation, observe that this quantity is what? This is exactly phi beta of s. So all of this is larger or equal to 2. Did I drop? Sorry, I did something here. Okay, I did something that I... let me... Okay, so here I should say there is a sigma 0 plus beta divided by sigma y plus beta. I cannot drop this... and here, okay, the sigma y beta outside is not a good thing, so this guy was here. Okay, so this was jxy sigma y plus beta. Okay. Sorry. There was still these terms. But the important thing is that we are in infinite volume here, right? So this quantity is 1. Just so this guy disappears. So it was important to multiply by the sigma 0 to make this guy disappear. And now you get, so 2, sum for s containing 0, you get phi beta of s. You get something, sorry, it's not exactly phi beta of s because you get the jxy, and it was hyperbolic tangent of jxy beta. So you can easily check that it's larger or equal to this divided by beta. Hyperbolic tangent of x is larger than what it should be. And here, now what do you get? I'm going to write it like that. I'm going to write it as a probability. I'm going to put empty set of s delta equal s. And this is what? This is the law of the trace of n1 plus n2 hat. Remember the notations. That means the trace of the sum of two currents where n1 and n2 are sourceless. Why did I write it like that? Because here, you see, if you put the beta in front, you recover exactly the structure that you had for percolation, which was the sum over the set S containing 0, phi p of S, times the probability that the set S delta is equal to S. For percolation, it was not S delta, it was a set of points that are not connected to the boundary, but really think of delta as your boundary point here. So it's really exactly the same structure. It's just that percolation, the role played by percolation, is played here by the sum, by the trace of the sum of two sourceless currents. That's all. But that's exactly the same structure. In particular, if you take the infimum here, so this is larger than 2 divided by beta times the infimum of the phi beta of S. And here you get, now you get the sum over S of S delta equal S. This is what? This is 1 minus the probability empty set of S of 0 is not connected by n, or it's 1 minus, so it's connected to G. You are summing over all the set S, which contains 0, so that means you are summing on all possible set S delta, which contains 0. So this is exactly saying this big thing this is just the probability that 0 is not connected to delta. Not to myself, use G next time. 0 not connected to delta, so it's 1 minus. What is this quantity? Well, you use the switching lemma. This is just sigma 0 plus squared. And that's exactly what we wanted. So this is the end of the proof. And I really want to illustrate, I mean, can look like black magic a little bit, this proof, right? I mean, how can we end up on exactly somehow the simplest equation we can think of? But really think of the interpretation of percolation. It is the same proof with the natural percolation associated to the Ising model, which is exactly the source of, the trace of the source of two currents. And you're going to see next week when I'm going to prove that there is continuity of the phase transition in dimension 3, that once again the source of, the sum of two currents is going to be really the guy playing the main role. What did I want to say? So as I told you, I cheated a little bit because I should have introduced a magnetic field to have exactly the inequality in the right direction. But otherwise, this part is exactly the same. You just replace, you get an additional edge, which is this magnetic field. But all the lines are exactly the same. I cheated in the second place, in fact, is here. Because, in fact, I need to work in finite volume. And then sigma 0 plus beta divided by sigma y plus beta is not 1. Because there is no translational invariance in finite volume. That's why you need to introduce this C lambda, which is the infimum of these guys. And you get a C lambda, which appears here. But this C lambda, because it tends to 1 when you take larger and larger graphs, it's not going to give you any problem at the end. So this is not source of any additional difficulty. So that was the proof. And really think, if you want to explain it to your kid or to your boyfriend, I don't know, and just say, well, it's the same thing I already explained to you last week. The percolation one, it's the same, right? Just do that. If he didn't leave after the percolation one, I'm certain he will not leave now. Okay, that's the end of this thing. What did I want to say? Okay, so let's start. Actually, maybe let's start the other one. Let's start the proof of continuity. I'll try to tell you the beginning, and then like that, maybe I can actually give you all the details like that next week. Okay, so let's try to do that. So this is going to be 4, and it will be almost the last section. I don't know whether I will do an additional class or not. Maybe I will prove to you triviality in dimension 4 and more. I'm going to see. So CAT is continuity of the phase transition in dimensions 3 and more. So I'm going to put 3, but it works in any dimension, and I'm going to do it in any dimension. Okay, the theorem I'm going to prove is the following. It's going to be, it's not, you're going to see at first it looks a little bit weird. So let's think of what happened for Potts model in 2 dimensions. When the phase transition is discontinuous, what happens? We have 2 different, actually, we have Q plus 1 Gibbs measures when it's discontinuous. We have the measures with monochromatic boundary conditions at criticality. But we also have the free boundary condition, which is not the same because remember, they are obtained from, the free boundary condition is obtained from the random cluster model with free boundary condition. And the other one, the monochromatic, they are obtained from the wired. infinite cluster with color K, all the others uniformly. So we see very well the difference between the different measures, right? Okay. But what I really want to illustrate is that there is a free state and then there is the other ones in the case of discontinuous phase transition. So the difficulty, if you want to prove continuous phase transition, is basically to prove that the free state is the same as the monochromatic one, which for Ising corresponds to, say, the plus state. The minus state is just minus the plus state. So our goal is to prove that the free state is equal to the plus state. What I'm going to do, the theorem I'm going to prove is in fact a little bit weaker than that, and then I'm going to explain to you how you imply it. I'm going to say if something happened for the free state, then it's equal to the plus state. And the very strange, you are going to see it's a very strange thing. So we are going to say if the infimum of the sigma 0, sigma x, and actually I'm not going to even look at beta c. I'm just going to look at some beta. If the infimum over all the x in ZD of sigma 0, sigma x, beta with the free state is equal to 0, then, and let's say I'm going to put it with a plus, okay. In fact, the theorem is going to be that the plus state is equal to the minus state, and it's equal to the free state. So it's a little bit strange. It says if the free state is disordered somehow, you agree? I mean, this means, this condition is basically telling you there is no long-range ordering. Sigma 0 and sigma x, they forget about their respective spins. They are asymptotically independent. If there is disorder, then, in fact, the plus state is also disordered because it's equal to the free state. So here it should really strike you as something very strange, because for the Potts model, when you have a discontinuous phase transition, what happens for the free state in 2D? You have exponential decay of correlations. So you have very strong disorder, extremely strong. It decays, this quantity decays exponentially fast in the distance. Well, what I'm telling you is that at least if I would be easing, this would imply that the plus state would be equal to the free state. So it's very strange. It's telling you that, you expect, in fact, you expect that if you would have a discontinuous phase transition, indeed you would have a very strong disorder for the free state. And I'm telling you, for easing, if you have disorder for the free state, then you have a continuous phase transition. So it's kind of counterintuitive. And it's counterintuitive for a good reason, that it's indeed what is happening. Like, I'm not telling you, no, I didn't write. So this obviously implies at criticality that you have, I'm always talking at criticality, even though it works for every beta. But I'm not telling you the Ising model has always a continuous phase transition, and there is a good reason for that. That if you take Ising on Z with Jxy equal 1 over x minus 1 squared, then the phase transition is discontinuous. Then sigma 0 plus beta c strictly positive. So there, something very strange happens, is that it's also, for the free state is ordered at the critical point. So this is very different than what you see for disordered phase transition on Z2. For nearest neighbor. Okay. It's sometimes called a towerless effect, this thing. Okay, so it is a conditional result. Now, how do we imply, how do we deduce from this theorem that you have continuous phase transition in Z3? So this is going to be due to something that you will hear about several times, I think, in all your respective talks on your articles. It's due to the infrared band. So for the nearest neighbor, . Ising model on ZD, D larger or equal to 3, we have the following magical inequality somehow, that if I look at the spin-spin correlation and that I remove just the average of the spins, then this is smaller or equal to, I think it's 2 over beta, but maybe it's not 2 over beta or whatever. Ah, yes, so I forgot then to correct it. There was a 1 over beta in the, a factor 2 that I forgot in the lemma for the previous proof, sorry. So 2 over beta times the green function between 0 and x. So this is the expected number of visits to x of a random walk starting at 0. So this is called the infrared band. I don't really want to prove it to you, but just let me explain why it's not so surprising. I mean, one way of seeing that it's not so surprising is remember that the Ising model was, and the Gaussian free field were two models that were lying at the two ends of the same family of models, which was this 5-4D, these 5-4 models. So when I was taking sigma x, sigma y, but I was adding plus sigma x to the 4. And I was taking sigma x to be a real variable. So both were at the end of this family. And in fact, therefore, you can see that these models are not completely different. Like they are basically the same class of models. In fact, they also have the same scaling limit. Not the Gaussian free field, but all the 5-4 models. And therefore, it's not so surprising because you have this interpolation between the two that you can get from one to the other one. It's not clear why it should be less or equal and get probably, by the way, it's going to get, the correlations are increasing up to the point where you get to the GFF, for which the GFF, the correlations are exactly the green function. It's the definition of the correlation of the GFF. So it's not completely clear, but it's not the end of the world to actually believe that. I hope it won't be the end of your world. But, okay. So there is this magical inequality, infrared bound. And this infrared bound is therefore telling you well, it's telling you take beta smaller than beta critical. Let beta be smaller than beta critical. What do you get? The infrared band, in this case, the plus state is equal to the free state. This is in subcritical, it's trivial. So you get sigma 0, sigma x free beta. Then the average of sigma 0 in subcritical is 0. The average of sigma x is 0. So you get this smaller or equal to 2 over beta g of 0x. And now let beta tends to beta c from below. You are going to get exactly sigma 0, sigma x, beta c free. Here, there is one thing which is not completely obvious, which is that the free state is somehow continuous from below. But remember that the free state is the limit of the free state in finite volume. Because think, for instance, of the random cluster model. Think of the random cluster model. That's the best. Think of the random cluster model. So why is it true that when you increase P for the random cluster model, when P tends to PC, the random cluster model with free boundary conditions converge to the random cluster model with free boundary condition at beta c. Well, you can see it as the free boundary condition for the random cluster model is a supremum somehow of the measures with free boundary condition in the discrete. So it's the supremum of a supremum. You can interchange the limits, and in finite volume, it's clear that the free state is converging to, because just everything is continuous in the infinite volume. So the free state is continuous from below. You can guess how the plus state is continuous. It's continuous from above, because then it's the infimum of the infimum. So this is easy to get. So I get this thing. But now on ZD, the random walk is transient. Therefore, sigma 0, sigma x, beta c free tends to 0, because it's smaller than phi. So corollary, the phase transition is continuous for d larger or equal to 3. Let me finish the class by saying, here I did it for nearest neighbor. If you define long-range model, you can also define the natural random walk associated to this long-range model, which is to say that you jump from x to y with probability proportional to jxy. So you will tell me maybe the sum of the jxy over y is not finite. If it's not finite, you can easily check that the beta is 0. Beta c is 0. So it's not an interesting, all the regime we are interested in is sum of the jxy finite in y. Therefore, you can take this random walk and you can look whether it's transient or not. The conjecture is that as soon as it's transient, the proof should work. The only problem is that getting this inequality. What you would like to say is that for infinite range, this inequality is also true if you take infinite range, if you replace the Green function by the Green function not of the simple random walk, but of this new random walk, which is naturally associated to your model, to this coupling constant. Problem is that proving this thing, this infrared band uses what we call reflection positivity, and reflection positivity is not available for any jxy. So there are long-range models. In particular, if you take 1 over x minus 1 to some power, it works. So there are models for which you can also deduce similar results, but it's not all the models, unfortunately. So next week, what I'm going to do is I'm going to prove this. And you are going to see the proof is really involving percolation. And I think it should not take me the 2 hours, so probably I will also prove to you that the model is trivial in dimension 4 and more. Let me just tell you one thing. For the smartass that want to, that would like to prove that theta PC is equal to 0. So for Bernoulli percolation in these three, you do not have an infinite cluster at criticality. This is the equivalent of this result for percolation. But I really want to highlight one thing. This result is based on two things. You need to prove that you have disorder at the critical point for the free state, and you need to prove that the plus state is equal to the free state. The whole difficulty in this theorem is proving that if you have disorder for the free state, you have disorder for the plus state, because it's not obvious. This thing, the equivalent for percolation would be obvious. There is no, there is a unique measure. So for percolation, the difficult part is to prove that the free state somehow, is the equivalent of this part, that the free state is disordered. The point is that here, this infrared bound, which is the trick that allows you to do it for easing, is not available for percolation, and there is a good reason for that. It's just wrong. The inequality is not true for percolation. We expect the spin-spin correlation at criticality to have asymptotically to be bigger than the Green function, which would be in 1 over x. So this doesn't shed a new light on theta PC equals 0 for percolation. And that's something that needs to be highlighted because that's the question I'm getting every single time I present this proof. Okay, so that doesn't show anything, doesn't help, doesn't not help. I mean, it doesn't, it's just independent of the other guy. So you will have to come up with a better idea for theta PC equals 0. And we see each other next week. Thank you.